Bless you. MHC1 and MHC2. MHC1 is a self-receptor, but we can take an infected aspect of ourselves and post it up and say, excuse me, sick. Okay? MH2 is antigen presenting, just straight up antigen presenting. They engulf it, they present it. Well, here's what we're looking at right now. Phagocytic antigen presenting cells. What are the three types of antigen presenting cells? Oh my gosh, Susan. Give me one of them. Macrophages. All right. What's the other one? Dendritic cells. And then possibly B cells. Okay? So notice phagocytic APCs engulf extracellular pathogens. Just gobble it up. Once we engulf it, then what are we going to do? We're going to take a chunk of that and say, hello, what T cell does this belong to? It's literally as simple as that. Now, I keep demonstrating that in the classroom, but literally that's what it does. It engulfs it. It's going to load it. It's going to load it onto a class 2 MHC protein. So like anything, proteins have to be there, period. Very few things are free-floating. Very few things. Almost everything is loaded onto a protein. And in this case, we do. We load it onto a protein, we move it up to the surface, and we present it. Notice number 5. It says antigenic fragments. Antigenic, that means it's actually going to or can produce an immune response. Antigenic. And you know what? Your guys' worksheets, I noticed that some people didn't do that section. Unfortunately, I told you it was graded, so you're not getting just an overall point. But what did it say on there? It said antigenic. Antigenic? That means that it's got to bind. It's got to have a certain binding point. And there are multiple binding points on there. Okay? Antigenic presentation. Can we put that key into that lock? Now, here's something. Can you put certain keys, like Schlage? That's a brand name. Can you go up to any lock that's like that and put it in there? You can. You actually can. As long as the lock is matched up, the key will insert. But can you turn the key? No, you can't. And that's exactly like this. Antigenic determinants determine whether or not that antigen binds to the appropriate T cell, binds to the appropriate cell. So seriously, I'll show you guys something here. Every single one of these keys are the same. I can go around to any lock on campus and they will go in there, but they won't open it. Only the right key determines which door I can open. You guys get that? Antigenic determinant. Only the right key determines it. But I can take any of these keys and go to any door in this building, especially, slide the key right in, but it won't open it. It has to be the right one, and that's what they're saying. When we bind it up there, we're presenting it for the right antigenic determinant, the right spot. And everything is like that. Remember, it's one T cell and one B cell that we have to line up with, and that's what this antigen presenting cell is doing. It's lining up with that one T cell and one B cell. Remember, this is adaptive. It's very specific. So it literally has to find that one, line up with it, and then go from there. Now the great thing is once it starts multiplying, don't we have a bunch of them out there? We do. Okay? So phagocytic APCs, free and fixed, Kupffer cells, microglial cells in the brain. We already know these. These are macrophages, just special names. Then non-phagocytic APCs, Langerhans cells and dendritic cells. Okay, now the ones that I've said let's focus on, unbelievably Langerhans cells got changed to dendritic cells. So if you look it up in certain books, they're actually going to say dendritic cell, Langerhans. It's the same thing, literally. And now they're just giving it different names because, first off, it's in the skin, so where's it found? You know, so they're saying, oh, okay, we have dendritic cells that circulate, but then we also have dendritic cells, Langerhans cells, that are found in the skin. And it was just Dr. Langerhans that actually identified them. And so in this case, they're just saying, okay, you know what, it's Langerhans cells and it's found in the skin. Is it important to have an antigen-presenting cell in the skin? Yeah. Yeah, cut my pinky. Yeah, it's very important to have it in there. Antigen recognition, well, inactive T cell receptors recognize class 1 or class 2 MHC proteins. They recognize a specific antigen. Very, very specific. 1. Cur1. Cur1. Okay, binding occurs when MHC protein matches the antigen. It has to match up. It has to be the same thing. CD markers. Now, we talked about this, didn't we? Did we make it to CD markers? Good, good, good. Okay, CD4 and CD8 are the ones that we're going to focus on. There's a lot more. Okay? CD8 markers found on cytotoxic T cells, MHC1 receptors. CD4, MHC2 receptors. A CD4 is a helper cell, helper T cell. This is the most important thing to lock down right here. Which CD4 marker, important markers, which one is part of which one? CD8, cytotoxic T, suppressor Ts, class 1. CD4, class 2. Okay? You have to know which ones they line up with. Now, CD8 and CD4 markers bind to CD3 receptor complexes. Okay? Prepare cell for activation. Now, when they say prepare the cell for activation, let me give you an idea of how this works. Okay? It's really interesting, but it's a crazy idea. It's a really, really crazy idea. So this half of the class, I'll have to turn this way. Obviously, you guys are sitting where you're supposed to. So let's do this, okay? There you go. You're a T cell. I'm an antigen-presenting cell, okay? I'm going to need your help, too, okay? I know you don't have to get up. It's okay. All right, let's do this. So I have a match, okay? I engulf this. I present it, MHC2. Okay, I come over, and I'm like, oh, that's a match, right? Hi there. And then, here's what you're going to do. You're going to say, go ahead and multiply. It actually takes multiple steps. It takes additional cells, including B cells. It takes an identification handshake, and this to activate that cell. Now, why do you think we have all those checks and balances in place? Anybody? Why do you think I have to first find her, then I have to make sure she's the right one and shake her hand, and then someone else has to say, go ahead and multiply?
To make sure that it's the right one.
Exactly. We have to make sure that we're not going to arbitrarily activate a T cell, which is going to mount a massive immune response against her own body. Because remember, when she starts to multiply, it's out of control. Can you palpate your lymph nodes when you have a flu? Yes. Imagine if she got activated and you didn't have anything. Imagine the devastation that's going to occur if she gets activated and you don't have an antigen. You don't have anything wrong with you. Imagine if she gets activated and it's an antigen in your body that's yours, and she acts against it. It's devastating. It'll kill you. It's a systemic attack against yourself. You're done. So we have these checks and balances in place to prevent her from doing just that. Because even if it's close, what if I handed a green pin? She's like, it's kind of close. I'm going to activate myself. I'm going to self-activate. What if the green is your liver? What's she going to attack? Every single liver cell. Is that good? No. So we have to have these checks and balances. We have to match up. It has to be right. I have to say, okay, yes, you can go ahead and do this. And then she has to say, go ahead and do it. There's actually multiple checks and balances. There are other cells around saying, it's okay, go ahead. Okay? And that's what they're talking about. This CD3 receptor complex prepares the cell for activation. So we can't just like, oh, okay, cool, here's this, click, let's go. It's an actual, we're preparing that cell. We're saying, you know what? It takes all these checks and balances to get this right. So now, what we have to think about in our heads is, wow, that actually makes it really difficult for a doctor to figure out how to treat specific diseases when we have a problem. Because it's not just one cell to one cell, let's bind and then let go for it. It's a whole list, a whole laundry list of actually checkoffs that you have to do before that cell is activated. So when a scientist or a physician is trying to figure this out, they literally have to say, okay, that's the cell that's going to activate, this is the cell that's going to help. How do they bind and what receptors and how many receptors and how many complexes do we have to activate to get that cell to go? It's craziness, and we're going to learn a little bit more about it. Now, we're not going to go into any depth, like major depth, on how all of that occurs, just kind of some minor stuff, some binding, some activation. And I know the minor stuff's still going to seem overwhelming, so I'll do my best to explain it. But the idea is that no one cell can just be activated from one antigen. You have to have a series of events. Okay? So, co-stimulation. Wow. Okay, Mabel, that's what you were. You were the co-stimulation. Were you right beside her? Yes. Was I activating her? Yes. Did you say go ahead and multiply? Yes. So, for a T cell to be activated, it must be co-stimulated by binding to stimulating cell at the second site, which confirms the first signal. So let's do this again. So check this out. Here you go. I'm an antigen presenting cell. I come up. Yes, that works. Hi, you ready? Multiply. Yeah, actually, she has to be co-stimulated. Does everything match up? Is everything good to go? Because if we unleash her, troubles. Okay? So co-stimulation has to confirm this situation. Has to say yes, 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 go get it. It's foreign. Now, activation of a CD8 activated by exposure to antigens on MHC. One responds quickly, producing cytotoxic T and memory Ts. The other responds slowly, producing suppressor Ts. So why do you think we're going to act quickly and get our cytotoxic Ts out there, but then go real slow for the suppressors?
Make sure.
See what cell they should attack to make sure.
Everything's going smoothly.
Okay, so check this out. Make sure everything's going. See what you guys are actually on the same exact page. You just have to put them together now. First off, let's quickly activate the people that need to go out and kick some butt. Go out and beat up those foreign cells. Let's activate them right now. And they're aggressive. They're like, rawr, let's go get them. And they're out there and they're tearing it up and they're beating them up and everything like that. But don't we know we have to slow that cell down? And don't we know that it has to actually understand what it's attacking, so we've got to slow it down while it's attacking what it's supposed to attack? So I'm going to activate you. You're going to get up and you're going to run out and you're going to start attacking everything. After you start attacking, then I'm going to say, you know what? I think you need to go calm her down. So I'm going to slowly activate you. And after she's created enough chaos and mayhem and beat all these other cells up, you're going to get up and go over. It's okay. Find your chi. Relax. Suppress, dude. Right? That's what you're going to do. So let's activate the cytotoxic Ts. Let's activate the memory Ts. Let's get them out there. Get them doing their job. But then we know, because if they're out of control, we need to calm them down. Yo, dude. Just give her some bait, man. Just chill. We're going to calm her down. But we're going to calm her down after she's been activated. Okay? So that's what they're saying. We're going to kick in the suppressor Ts. The great thing is that at the same time that we do this, you know what she's attacking, so you know exactly who to go up and who to talk to and who to suppress. What's that?
That's the main thing. Power of fireworks. Like, you know when to stop.
And yeah, exactly. We know exactly when to stop. And sometimes we need some help because Louisa, she's wily. When she gets out there, she starts breaking stuff. Okay, we're talking bull in a china shop here. She's just tearing it up. Okay, so we really do need Desiree to come over and be like, whoa, let's go vape, man. Yeah, we need to calm her down. Okay? Do you have a question?
Why don't the person slow down slowly down after?
So if we activate the suppressors right away, it'll be like Desiree saying, don't go and do it. It would actually be Desiree holding on to her, preventing her from doing her job. So by activating her first, she goes out and does her job, and then Desiree goes over and says, slow down. But if we activate them both at the same time, Desiree's going to walk up to her and go, you know what, you don't need to clean house. Let's go. Let's go party. Let's go vape. So literally stops her before she goes out and does her job.
You're first beginning the antigen, and then you're making a record, and then you're calming
Yeah, well, yeah, so we present the antigen to the cytotoxic, which gets her super excited. Are you excited? She's totally excited, look at that. Yeah. Okay, so she goes out and she does her job, but then we need to actually suppress her because the last thing we want is her getting overexcited and attacking Roberta. Because that would just be really weird, like, rah! And we're like, no, she belongs. Yeah, so literally we send her out to do her job, but then we have to suppress her. We have to stop that immune response because it can get out of control. Now remember, this is a big one to remember. In any immune response, it doesn't matter what it is, there's always collateral damage. We're always going to destroy our own cells in the process. Especially the chemicals that are released. You're going to be releasing chemicals to call in more cells. Those chemicals are actually deadly to our own cells. But we kind of chalk it up as part of doing battle, right? Like we're going to ruin some of our cells, but in the long run, it's beneficial to us. If we don't stop her, we're going to keep ruining more of our cells, and that's where you come in. Prevent her from ruining even more cells. Because literally, when we start battle, unfortunately, there are some of our own cells that are going to get damaged. So let me give you an idea of how this works. Okay, so we unleash cytotoxic T cells on your throat, and they start battling all of the viruses that are in your throat. At the same time they're killing throat cells. It's just one great big giant battle going on in your throat, and it's actually killing throat cells. By the thousands of them, it's killing them. Because it has to kill everything in that area until it's specific. And once it's specific, then it'll kill some, but not as many as it was before. Because the chemicals are killing a lot. And how we know that is when you're done being sick and you're in the shower and you go, what comes out? That's all cell. Mucus, pus, debris, cells, your own cells coming out. Because unfortunately, some of them did die in the process. And that's what the suppressor cell's there for, is to stop her from doing that after everything's been done. So really to suppress her and say, okay, the immune response is over, let's stop. Because if it gets out of control, man, oh man.
It's related with the cancer. That's why the suppressor doesn't do the job as quick as it's supposed to be.
Well, no, cancer, the thing with cancer is it's so fast we can't keep up with it. Yep. Okay, so let's take a look. Cytotoxic T's seek out and immediately destroy target cells. They release perforin, and we know what that is. What did I tell you to call that? Yeah, poke holes in. Poke holes in. So if it's releasing perforin, it's poking a hole in a bunch of stuff. Okay? Secrete poisonous lymphotoxins to destroy target cell. Activate genes in target cells that cause the cell to die. So guess what? Yes, we're attacking, but we're also damaging other cells at the same time. I mean, we're very specific, but there are some collateral cells that are going to die in the process because of the chemicals and because of what's going on. And that's what Desiree's here for, the suppressor cells, to say, after you've done your job, Louisa, stop. You don't need to do any more. Okay, and this is the binding. Okay, so there's the CD8 protein, there's the antigen, the T cell, the MHC cell. Notice that it is an infected cell, so it's class 1. It's an infected cell, so it's class 1. Let me say that one more time. It's an infected cell, so it is a class 1. Okay, antigen recognition, co-stimulation, activation and cell division. Let's walk through those steps again. Antigen recognition, co-stimulation, and then KRPAL, activation and cell division. And remember, we're not just dividing into 1 or 2 cells, we're dividing into thousands of cells. So it's no surprise why our lymph nodes are so swollen. Okay? So, destruction of the target cell, literally we're going to lyse the cell. We're going to poke holes in it and it's going to die. It's going to blow up. Memory T cells, well, produced by cytotoxic T's. They stay in circulation, immediately form cytotoxic T cells if the same antigen appears again. It has to be the same one because it's memory. It has to be the same one. Okay? So because it's a memory T cell, it's going to stay in circulation, and the next time that we come in contact with that same exact pathogen, we'll be able to fight it off in no time whatsoever. The attack will be a lot larger and more precise, less chemicals. It will actually take a quarter of the time to destroy it. In fact, by the time you feel symptoms, it's already over with. Because you've already mounted a huge response because of your memory cells. Well, suppressor T cells secrete suppression factors, inhibits response of T and B cells, okay, act after the initial response. Limit immune reaction to a single stimulus. Because we know that once you get Louisa going, oh dear, she's out of control. She's going to trio, she's tearing things up, she's knocking tables over. Yeah, she's crazy. Crazy. So we need Desiree. We do. Okay? Activation of CD4 T cells, helper T cells. Okay? Memory helper Ts. So here you go. Here's your class 2 MHC. There's your helper T. There is a co-stimulation on that. Okay? And we're going to activate that cell, and that cell is literally going to go after the same pathogen. Okay? Now, it's called a helper T for a reason, because it can do a bunch of different things, including co-stimulation, activating B cells, work with B cells. Okay, so here, active T cells, active T cells secrete cytokines that stimulate both cell-mediated and antibody-mediated immunity. So, what cell is an antibody-mediated immunity? Yeah, a B cell. So literally, helper T is saying, you know what, Louisa, go play. Go on, go destroy things. But Amina, I want you to help her. I know you're a B cell, but you know what? Secrete those, make plasma cells, and then secrete the antibodies. Okay? So you're gonna fling antibodies everywhere. That sounds like fun. It's like playing in the mud. Just throwing mud everywhere. Yeah, I'd do that. I totally would. 4 functions of cytokines: stimulate T cell division, produce memory T cells, accelerate cytotoxic T cell maturation. Okay? Attract and stimulate macrophages, attract and stimulate the activity of cytotoxic Ts, and then promote activation of B cells. So what do helper Ts do? Everything that pretty much our immune system, right? Yeah. And if they don't work, if they're infected, do we have an immune response? No. No, not at all. Okay, so here you go. Antigen bound, class 1, indicates that the cell is infected, otherwise an abnormal cell. Okay, CD8 T cells, cytotoxic Ts, memory Ts, and suppressor Ts. Perfect. Class 2, helper Ts, memory helper Ts, and what are they going to do? They're going to stimulate the immune response. Hence their name, helper T. They're going to stimulate the immune response. B cells, well, we know that they differentiate into what? What do B cells become? Plasma cells. And what do plasma cells secrete, Amina? Plasma cells secrete, she said antibodies, just saying. Okay? Now it says responsible for antibody-mediated immunity, attack antigens by producing specific antibodies, millions of populations, each with different antibody molecules. Okay? Oh, look at the clock. That makes me look like you want to leave. You don't like my presence. I like you. I even use you as an example. That's like admiration. Okay, B cells, they do become sensitive to corresponding antigens in interstitial fluid. B cells prepare for activation. Okay, during the time that they become sensitive, antigens are taken in to the B cells, processed, reappear on the surface, bound to a class 2 protein. So what is that saying? That a B cell can become a antigen presenting cell. Okay? So there's your antigen. Okay, it binds to the B cell. Okay, the B cell's sensitive to this. It can present that antigen. But what's so important about this is that when the B cell becomes active and it differentiates into a plasma cell, the antibodies are the same shape as the antigen. Yeah. So when we secrete antibodies, okay, what do you think they're going to bind to? Which of these antigens do you think they're going to bind to? The star. Yeah, they're going to bind to this. So when the antibodies are released, what are they going to bind to? The exact antigen that started the process. Let me back up one slide. That antigen that started the process, it's going to bind to. Now, are we limited to 1-to-1 every single time? No, you could have thousands of these chain reactions going on in your body all the time. You could be fighting off 4 or 5 different foreign pathogens and not even know it. Never even know it. Probably not even have a sign or symptom because your body's, the pathogen's so slow that your body's like, I got this. You don't even feel it. But in other cases, they can be a little bit faster and you do feel it. Oh, back up. So helper Ts help the B cells. They prepare them for activation. We need the helper Ts for this to occur. B cell activation, helper Ts binds to the MHC complex, secretes cytokines that promote B cell activation and division. So we need the helper Ts. So is there a cytokine co-stimulation there? Yes. Class 2 MHC receptor, T cell receptor, antigen in the middle. We bind to that B cell and we activate it. Now, B cell division, activated B cells divide into plasma cells and memory B cells because they're extremely important. We need it again if we have the same attack. And take a look at this. Look at all the antibody production. It's going to circulate around. It's going to bind to the foreign pathogens. And what was the one thing that helped with the antibody binding and the process that occurs afterwards? Wow, you look really nice today, Louisa. What is that? Thank you so much. It's a compliment. Yeah. It's a compliment. It's a compliment. Kara's like, I love how it was just kind of like this monotone compliment. It was a compliment. Okay, and remember we have interferon and complement. What does complement do? Well, it complements the reaction. It complements what's occurring. It helps to the binding. It helps with the activation. It helps complement the reaction. What's going to happen? So plasma cells, they secrete antibodies. Memory B cells, okay, like memory T, they remain around for the next infection of the exact same antigen. It has to be the same one or they'll never get activated again. Antibody structure. Well, there are 2 parallel pairs of polypeptide chains. I love saying that. Lots of P's in there. Okay, 2 parallel pairs of polypeptide chains. That's so awesome. Okay, there's heavy chains and light chains. Okay, each chain contains a constant segment and a variable segment. And this was on your guys' worksheets. Okay? It was on. But we're not going to worry about the heavy and the light. What we're going to worry about is this right here. Okay? And guess what? We have plenty of time to go over this. I'm going to help you with this. Please don't take this in a derogatory manner. It was the best way I could figure this out. Besides, I actually have a friend named Gabe. I have a friend named that, so don't even, you'd be like, he said, don't. It's silliness, okay? There you go. Now, it's not in the same order that's up there, okay? So we're going to make this quick, and we're going to see how many people remember this tomorrow, because we might, I know we're not going to get done today, so literally we are running behind, but don't mess, and there's a little with, right here, gay, G-A-E. Don't mess with gay. Don't mess with gay. Okay? Don't mess with gay. Don't mess with gay. Don't mess with him. Because you know what? He's got antibodies on his side. Okay? Don't mess with gay. Now that's how I remembered it, but then I added a little playful thing to it, and you can do whatever you need to do. D-M-G-A-E. Don't mess with gay. It's the best way to remember it. Remember, it's I-G-D, I-G-M, I-G-G, I-G-A, and I-G-E. Now, two of them you should already know, but how about this? D to the B. Okay? That means it's part of the B cell. It's part of B cell activation. D to the B. Okay? Must be first. Must be first. This one has to be the first one out there. It's part of the initial responses all the way across the board, so it must be first. This one, guard the fetus. This is the one that crosses the placenta. This is the one that moves across the placenta and gives the fetus its immunoglobulins. It gives it its immunity. Remember we said that it's transferred from mom to the baby? It does a lot more, but this is one of the best ways, and I think I misspelled guard, but I don't know. I'm just, yeah. Apple juice. What? Yeah, because how about this? Milk, sweat, gastric juices, anything liquid has an IgA in it. Didn't I say that the immunity is transferred from mom in breast milk? Right? So anything that is a juice, apple juice. I'm talking about gastric juices, I'm talking about sweats, I'm talking about saliva, I'm talking about milk, anything that's liquid, IgA. And then, because when I took this, I had a professor, okay, and he was kind of an interesting fella, okay, and I had to learn from him, and his name was Jim Ellinger. And because I couldn't think of a good one, I said, this is allergies. Allergies. And it sounds like what? Allergies. And what do we secrete during allergies? Histamine.
Wow. What a great story.
Histamine. Okay? This is how I remembered it. Now, if you need to change it for your memory, for the way you would do it, go ahead. But you know what? D to the B. Must be first. Guard the fetus, apple juice, and allergies. And because it's allergies, we know it's histamine. Basophils and mast cells. Because it's apple juice, gastric juices, mother's milk, sweat, saliva. Guard the fetus. It's all about the placenta. We've got to cross that placenta. We've got to get over there and protect. Okay? Must be first, literally. M is the first one on the scene every single time. And then D to the B. Wherever there's a B cell, there's an IgD. Okay? So let's see what this says. It's crazy, but unbelievably it sticks. Don't mess with gay. Okay, they do bind. They have different binding sites. Antigen body or antibody complex. Antigen, foreign antigen, antibody. They have to bind. Okay? they have at least two antigenic determinants. Antigen, determine. Which antigen do we bind to? Determine which antigen we bind to. We have to determine which antigen we bind to. So they have antigenic determinant sites. Okay? Now, when B cells become sensitive to all of this, exposure to complete antigen leads to B cell activation and immune response. So, the B cell binds to an antigen. Okay? The B cell binds to an antigen. Then it creates plasma cells, and plasma cells create antibodies. Those antibodies match up to that antigen. Now, we have other antibodies also, okay? But we have to activate the B cell. We do have a determinant. Determine which one. Now, we're going to end with this term, hapten. Hapten. Hapten is a partial antigen, must attach to a carrier molecule to act as a complete. So, a hapten is an incomplete antigen. Let me say that one more time. A hapten is an incomplete antigen. Why do we have these? Well, guess what? Dangers of haptens. Antibodies produced will attack both hapten and carrier molecule. If the carrier is normal, okay, antibody attacks the normal cell. For example, penicillin allergies. Pretty much, you might as well just say allergies, allergic reactions. Allergic reactions, and hence the reason why they say, guess what? Are you allergic to anything? Because 9 times out of 10, it's a normal carrier, but your body thinks it's abnormal, so what does it do? It attacks it. And that's why people are allergic to penicillin. Because your body thinks it's foreign, even though it's good for you. Even though the carrier is good for you, it thinks it's foreign and attacks it. Okay? So we're going to stop right there.